vectors can be used to describe geometric objects. In this video, we'll look at how we can specify a straight line using an equation involving vectors. So, say we have two vectors, A equal to A1, A2, A3, and B equal to B1, B2, B3. Here we're using column vector notation, which we discussed in a previous video. One way to specify a straight line P is with the vector equation P equals A plus lambda B, where lambda is a parameter that can be any real number. Note that P is just a vector. Written as a column vector, it's A1 plus lambda B1, A2 plus lambda B2, A3 plus lambda B3. But as lambda ranges over the real numbers, we obtain an infinite set of vectors, the endpoints of which all lie in a straight line. Let's look at this for some specific values of lambda. So when lambda is 1, we get the vector A plus B. For the purposes of this example, we'll take A to be this vector and B to be this vector. With them placed end to end like this, we know that A plus B is this vector. What about when lambda is 2? Then we get A plus 2B. So we move along A, then along B twice. So A plus 2B is this vector. Remember, lambda can be any real number. So what about minus a half? So we travel along A and then along half of B in the opposite direction to B. So A minus a half B is this vector. So you can see we always move along A and then we move along some multiple of B. So we always arrive at a point on this line. Hence, the equation gives a specific line in 3D space. Note that using this method, we have specifically defined the line that passes through the endpoint of A. That's this point here, A1, A2, A3. And P is parallel to B. Let's look at another example now. Let's once again consider vectors A and B, and this time we'll let A equal A1, A2, A3 and B equal B1, B2, B3. Note the subtle difference here. The lowercase boldface a is a vector. It has a length and a direction, and can be represented by a directed line segment. The uppercase A is just a point in space. You can think of uppercase A as the endpoint of the vector A when the vector A is in the standard position starting at the origin. The vector A is sometimes called the position vector of the point A. And of course the same applies to B. So the question is, what is the equation of the line that passes through both A and B? Let's draw it. We'll take A to be this vector and B to be this vector. So then this is point A and this is point B. First of all, let's figure out what this vector here is. Well, to get from point A to point B, we'd move along vector A in the opposite direction to vector A, and then along vector B. So this vector here is minus A plus B, or, to put it a bit neater, B minus A. We're looking for this line here, so, using the previous example as a guide, we can deduce that the line is given by the equation P equals A plus lambda B minus A. If we multiply out the brackets, we get A plus lambda B minus lambda A. Rearranging and factorizing gives us lambda B plus 1 minus lambda A. This is the standard way of representing the line, but note our choice of A here was a little arbitrary. The position vector of any point on the line would work just as well. So what if we took B instead? Let's try it. Let's take the equation Q is equal to b plus lambda b minus a, which equals b plus lambda b minus lambda a, which is 1 plus lambda b minus lambda a. Though these two equations are slightly different, they actually specify the same line. You should convince yourself of this by plugging various different values for lambda into the two equations and seeing what vectors you obtain. Let's sum things up now. So, if we have two vectors, a and b, then the equation of the line p through the endpoint of a and parallel to b is p equals a plus lambda b. And the equation of the line q through the endpoints of a and b is q equals lambda a plus 1 minus lambda b.
I and his happiness